Hey, AP Chemistry, how are we doing today? So today our plan is to go over ionic bonds. So for that, what you're going to need is you are going to need your notes and something to write with, and then you might need a periodic table. So if you got one, go ahead and pull that out. If not, you can always Google one or pull one up on the Canvas page. But let's go ahead and get started with this. So we are continuing our unit on those types of bonds that we've talked about, right? So we've talked about metallic last class, and today's actually going to focus on our ionic bonds. So let's actually take a look at what an ionic bond is. First off, an ionic bond is a bond that forms between a metal and a non-metal. And this really does fall on their differences in electronegativity. That's the reason we see these bonds actually starting to form. Basically, what happens is that metals or cations tend to lose electrons easily, and that they lose them to an atom that has a high affinity for those electrons, so electron affinity, right? And then that charge is what kind of holds them together. Now, we talk about losing electrons with ionic bonds a lot. So my question is, do atoms actually truly lose, meaning they don't have any attachment to them anymore, lose their electrons? No, they don't, right? They don't lose them entirely, because if they did, there wouldn't be anything to hold those two atoms together anymore. So what happens is one electron gets pulled closer to the other side, closer to the other atom. And that's where we see that charge start to form, right? Okay, so we see that attraction with those electrons. Now, ionic bonds are going to form because that pair has a low energy that separates the ions. And those bonds are going to form because they're basically trying to reach a lower energy level. Now, I don't necessarily mean like dropping down to a lower energy level in terms of like our quote-unquote electron cloud. But what I do mean is they're trying to reach a point where they are more stable. All right, so we're basically looking for these atoms to become more stable. And that's what we're actually seeing when these bonds form, right? They're trying to get that full valence shell, because at that point, those energy levels are actually more stable, which means it takes less energy to hold that all together. Okay, now here are some properties of our ionic compounds. First off, they are any solid that can conduct an electrical current when they're either dissolved in water or they're melted. Okay, so when they're dissolved in water or they're melted, they will conduct electricity. Other substances won't do that. Salt is an example of an ionic compound, sodium chloride, but that's not the only ionic compound that is a salt, because all ionic compounds are what we classify as salt. All right, so a salt is what we would call a ionic compound. Right, and so that's what you'll see a lot of times, is that we refer to any ionic compound as salt. All right. Another thing to note is that if I've got a polyatomic ion, polyatomic ions are actually held together by covalent bonds. But as a part of that covalent bond that forms, they have a charge, and so we call them an ion. Now, when those ions bond with another atom or another polyatomic ion, we form an ionic bond between them. So in the case of this, we call sodium sulfate here, we call it ionic, even though it's got 4 covalent bonds, because right here, the bond that would form between the sodium and the sulfate, that is an ionic bond. Okay, there's a high difference in electronegativity there. So even though there are more covalent bonds, because the sulfate is technically a covalent bond that's forming, even though there's more, we do call it ionic because there is that ionic attraction. There's that gaining and losing of electrons that's occurring. Okay, now when that gaining or losing of electrons happens, so when we form an ionic bond, we get what's called lattice energy. So lattice energy is basically that change in energy that's going to take place when I'm basically packing together my ionic compounds, right? So taking, for instance, sodium, so sodium as the metal, and I turn it into a gas. And then I take chlorine as a gas, and I put them into a confined area. So I have sodium gas and chlorine gas, and they're in a confined area. What happens? Well, they turn into what we would think of as table salt, so sodium chloride. And that sodium chloride is actually a solid. So I took two gases and I combined them together, and I get a solid. So that's what we see with this equation right here. So the sodium ion plus the chlorine ion is going to give me the sodium chloride, which is a solid compound. Now, one thing to note is that in that case, we are forming a bond, right? When we form bonds, that's going to be considered exothermic. We're going to release energy. So why do we release energy? Well, we release energy because the atom is actually more stable. So we already talked about that a little bit earlier, where as bonds form, right, they become more stable. So because they're more stable, they take less energy to actually hold together. And so that's what we're actually seeing when these bonds form, when we have these favorable conditions for bonds to form. They're actually going to take less energy to hold together than they would as their natural states. And so since they take less energy, they're going to release the excess, because any of the excess energy is just going to cause something to become more unstable. Okay? So if I've got bonds breaking, to break a bond, that's going to be endothermic. And if I have bonds forming, that's going to be exothermic. Okay, so if I have bonds breaking, that's endothermic. It means I have to add energy in to cause that bond to break. And bonds forming is just going to happen. And so it takes less energy to keep those together. And so because of that, it's exothermic. All the extra is going to be released. Okay, so when we're talking about exothermic, obviously we're going to be talking about the losing of energy. And so our energy will be classified with a negative symbol. And again, it's always trying to achieve the more stable form. When we are looking at the heat of formation, a lot of times we'll talk about what's called the Born-Haber cycle. And basically that's just going to be a theoretical or a hypothetical series of reactions to break it down into what's actually occurring. You might have done this when we talked about phase diagrams in the past, where you talk about, okay, to go from a solid to a liquid to a gas, it took this much energy to transition through those phases, and you add those energies. It's kind of the same thing. It's kind of along that same lines, except now we're looking at individual bonds. And so to create or break bonds, we're going to be taking different amounts of energy for that to happen. Right, to remove those electrons or gain those electrons, the first ionization energies or second ionization energy, anytime that happens, it takes different amounts of energy. And so you're going to be adding up those energies as you go. Okay, so that's what's called the Born-Haber cycle. And we don't really need to know how to do that for the purposes of this class, but you do need to know the concept of, as we're gaining or losing electrons, what's happening is we're going to be it's going to require some energy for that to happen, right? And we did talk about this last class with Coulomb's law, right? When we have the charges of different atoms that are forming a bond, we look at the radius between them, and we can actually use that for our lattice energy. If you'll notice, this is basically our Coulomb's law formula. What has changed, though, is that instead of our distance squared, we're using our r squared. And r squared is going to be the distance from the center of the cation and the anion. So it is very similar, but it is going to be slightly different in that case. Okay. Okay. So one thing that we can actually notice is that we can use pretty much Coulomb's law to determine how much lattice energy is there. Now, lattice energy is, again, just kind of that change in energy that we'll see that's when those bonds form, right? But it's basically a modified form of Coulomb's law. K is still the proportionality constant. The problem with K is it does depend on the structure of the solid and the electron configuration of the ions. But a lot of times you will be told what your K is, or you'll be solving for it. Q1 and Q2 are going to be the charge of the ions, and then R is going to be the distance from the center of the cation and the center of the anion. So instead of from the centers of the atoms, we're talking about the cation and the anion. Remember, that's going to change because when you gain or lose electrons, you're going to actually change the size of the atom as well. Okay? And when we're talking about ionic bonds, we do need to recognize that when we gain and lose electrons, we're going to have one thing that's positive and one thing that's negative. And since we've got a positive and a negative, when you multiply those two numbers, there's always going to give you a negative number in return. And so what that tells me is that anytime we're talking about an ionic bond forming, that's going to be an exothermic reaction. Again, because when we have those bonds and bonds are forming, that becomes exothermic. We lose that energy because it's no longer needed to hold it all together. Okay. So with our lattice energy, what we're going to see is that if I have an increase in my charge, for example, if I'm comparing sodium and magnesium, so they're both forming a compound with, let's say, chlorine. Sodium's got a charge of 1, magnesium's got a charge of +2, and then chlorine for both of them is going to have a charge of -1, right? If I'm comparing those things, as I increase my charge, I'm also going to be increasing my lattice energy. And so that's what we're seeing. And it's kind of like when we were talking about Coulomb's law. Well, it is like what we were talking about when we were talking about Coulomb's law. If we increase our charge, we're also going to be increasing that energy. If we increase our distance, we're going to be decreasing that energy. And since we're decreasing the energy, or since we're increasing the distance and decreasing the energy, we can kind of start to actually compare different substances and determine who's going to have or which substance is going to have a larger lattice energy. All right. There are some trends. That's basically what we were just talking about. So the forces of attraction between charged particles is inversely proportional to the distance. So basically, again, your lattice energy, if you've got a large distance, you're going to have a low lattice energy. All right. Inversely proportional. They're going to do the opposite of things. All right. So the larger the ion that we're talking about, so if I'm looking at like cesium or rubidium, those are very large ions. The larger the ion, the weaker the attraction. The weaker the attraction, the smaller the lattice energy. So your attraction is equal to your lattice energy. If you've got a high attraction, you've got a high lattice energy. If you've got a low attraction, you've got a low lattice energy. Okay? And then again, your charges are going to be directly proportional. So the higher the charges, the higher your lattice energy. Larger charge, larger attraction. Stronger attraction means larger lattice energy. Okay. And in the grand scheme of things, your charge is going to have a much bigger impact than your distance will on your overall lattice energy. Okay. So of the two factors, so of your distance and your charge has generally a more impactful effect on your lattice energy and over the attraction as well. Okay. Now, in the grand scheme of things, there probably has never been an ionic bond that is totally ionic. And what do I mean by totally ionic? Totally ionic would mean it's totally taking away the electron. If that happens, then there's no longer that attraction between them, right? We've pulled it completely away. It's not bonded anymore. But we do have a percent of ionic character is what we call it. Percent of ionic character. And that's basically just looking at, okay, well, what's actually occurring? Those electrons are slowly moving towards one side over the other. And how far are they moving? So that's what this next section is talking about. So this is a continuum of those bond types. And this is looking at their differences in electronegativity. So right here, if I'm looking at a nonpolar covalent bond, okay, so this is a pure nonpolar covalent bond, pure covalent. those electrons are going to be equally shared. And so we're going to see a difference of electronegativity that's very small, okay? So between 0 and 0.4. If we've got a polar covalent, now what that means is that those electrons are starting to be pulled closer to one side over the other. And so since they're pulled closer to one side, you're going to start to get some positive and negative charges on either end, slightly positive and slightly negative. Now this goes up to technically about 1.69 is where we're kind of sitting with our polar covalent bonds. And then if I'm talking about an ionic bond, that's when those electrons are going to be pulled much further to the other side, but you do actually still have that attraction there in the middle where that electron is still going to be pulled towards one side or the other, but it's not completely lost by that first atom that was holding it. Okay. Now, I was talking a little bit earlier about ionic character. Compounds with more than 50% ionic character, we consider them to be ionic. Now, what do I mean by 50% ionic character? I mean that it's basically pulling that electron 50% closer to the other thing. Okay, so we're pulling it really far away from the other atom, but it's still not completely lost. To be completely lost, which would be what we have with true ionic, we would have to take that electron completely away, right? And then that's where we see the electronegativity of about 1.7 is what we're typically looking at. So our range for electronegativities, if I have between 0 and 0.4, we call that nonpolar covalent. If I have between 0.41 and 1.69, we call that a polar covalent bond. And then last, if I have 1.70 or greater, then that's what we would call an ionic bond. And again, it's not 100% ionic, but it is what we would classify as an ionic bond. Okay. One thing to keep in mind is that when we're looking at electronegativity, there is a general trend that as you move from fluorine down, your general trend is that you'll decrease your electronegativity by 1. And as I move left from fluorine, I'm going to decrease by 0.5. Okay, so if I move over 1 from fluorine, it's going to be minus 0.5. So fluorine sits at 4, so the next one over would be 3.5. And as I move down, it would be decreasing by 1 each time. And that's a general trend. It's not perfect. There are obviously exceptions to it and that kind of thing. But if you're not given a chart or a table for electronegativity, this would be what you would need to use. Okay? All right. So now we know about ionic bonds in terms of how they form and that kind of thing. Let's talk a little bit more about our properties, and then we will wrap up our notes. So properties of ionic compounds. First off, they are very hard and brittle crystalline solids. Okay, so hard and brittle. That means they're hard, meaning they could actually be used to scratch something, right? It's going to be hard to actually, or their consistency is hard, right? And then if I've got brittle, what brittle means is it's easy to shatter. Okay, so if I take like a crystal of salt, sodium chloride, table salt, and I actually crush it with a hammer, it's going to shatter in a bunch of little pieces. That's what makes it brittle. Okay. Ionic compounds are all going to be solid at room temperature. It's just one of their properties. And so if you think you've got something that's ionic and it's not a solid at room temperature, then it's probably something else. Okay. Melting points are generally greater than 300 degrees Celsius. Now, again, room temperature is not 300 degrees Celsius. And so we will be seeing those substances sitting at a solid. All right. Our liquid state, so if we do heat it over that temperature, over its melting point, then we can actually see it start to conduct electricity as a liquid. But it will also conduct electricity if it's in water. Ionic compounds actually do not conduct electricity as a solid state, meaning if I take a stick of solid, a stick of table salt, and I stick it into a light socket, it's not going to shock me, all right, because ionic compounds do not conduct electricity as a solid. Now, if I took liquid salt, liquid sodium chloride, and I were to use that to pour into it, then that would, yes, conduct electricity, all right? If I'm talking about solubility in water, pure water actually doesn't conduct electricity. When I take some salts of different varieties, if I dissolve them into water, they will actually begin to conduct electricity. All right? Okay, so those are our properties. Let's kind of recap our naming, and then we will be done. So naming your ionic compounds. When we name ionic compounds, first off, remember that we have two parts of an ionic compound. You've got your cation, and you've got your anion. All right, so the example I'm going to give is sodium and chlorine. Sodium is going to be my cation, sodium with a positive charge, that's what makes it a cation, and then chlorine will be our anion. With a negative charge. Okay, so how do I name it? Well, the nice thing about ionic compounds is it is fairly straightforward. First off, we always name our metal. So our metal here would be sodium. And then our nonmetal would be chlorine. So I would do sodium and chlorine. But here's the difference. When you have an ionic compound, you change the ending of your anion, of your nonmetal. We change that to ide. So this would be sodium chloride. All right, so that's what we're looking for when we're naming it. Here are your rules for that. If we're writing the formula, basically you're just going to be making sure that you're canceling out those charges that we're working with. So if I've got magnesium and I've got chlorine, magnesium has a +2 charge, chlorine has a -1 charge. I like to say swap, drop, reduce. So what do I mean by that? So swap would be magnesium gets the 1, chlorine gets the 2. That's swap. Then we drop those numbers down. So magnesium gets the 1 there, chlorine gets the 2 there. And then we reduce if we can. Well, can I reduce a 1 and a 2? No, I cannot. So then our final formula would be MgCl2. All right, y'all, that is everything on ionic compounds. Please don't hesitate to reach out if you've got any questions. Hopefully y'all have a great rest of the day. Bye, y'all.